Okay, so in this video, I'm going to present a solution to a problem that showed up on the CMIMC, and it's sort of a counting combinatorial probability question, and I'm going to present a solution to it using a generating function and a root-of-unity filter. So the problem is that you have cards laid on a table, numbered 1 through 7, and you have a sequence of shuffles. And a shuffle is that you take one card that is not on the top. So in this case, it'll be anywhere from 2 to 7. So say you pick 4, and then you move 4 to the top and leave everything else unchanged. So if you pick 4, then it would go like 4, 1, 2, 3, 5, 6, 7. And so that's what we call a shuffle. It's a pretty bad shuffle if you ask me, but that's what we're considering. And we're asking, after 10 shuffles, what is the probability that top to bottom 6 ends up above of 3? So the first thing that you might think about when you're starting off this problem is to, instead of looking at 10 different shuffles, to just look at one shuffle and see what happens. So if we do one shuffle, then we can first try moving 2 to the top. And so you see that the relative positioning of 3 and 6 is unchanged, so 3 is on top of 6. Or we can move 3 on top and 3 is still on top of 6, or 4 on top, 4 is still on top of 6. 3 is still on top of 6. And if we move any card except for 6, 3 will still be on top of 6. However, if we move 6 to the top, then it'll become like 6, 1, 2, 3, 4, 5, 7. And so in that case, the 6 will be on top of the 3. So what does that mean? Well, we have 6 cards to choose from, which are 2 through 7. So there are 6 of them. And if we pick any 5 of them that aren't 6, so with a 5-6 probability, 3 is on top. And if we pick the 6 cards, so that's a 1-6 probability because there are 6 cards 3 to 7, then the 6 is on top of the 3. And so now you say, okay, so that's one shuffle. After one shuffle, you have a 1-6 probability of 6 being on top. So what happens after 2 shuffles? Well, let's choose one of these. So let's say that like we move 4 to the top. So that's something like 4, 1, 2, 3, 5, 6, 7, right? And we can play the same sort of game and ask what happens if we move different cards to the top from this position. So we can choose to move, say, the 2 to the top, and that becomes 2, 4, 1, 3, 5, 6, 7. Or we can move, like, say, the 5 to the top, that's like 5, 4, 1, 2, 3, 6, 7. And again, if you move anything except for the 6, the 3 is still on top of the 6, right? Because nothing here changes unless you move the 3 to the top, in which case it's still on top. Or if you move the 6 to the top, in which case the 6 is on top of the 3. So here, again, with the 5-6 probability, the 3 is on top. And with a 1-6 probability, a 6 is on top. And so here we took one particular case, but you can easily convince yourself that this same sort of thing works with any sort of arrangement after the first shuffle, as long as it's not the 6 on top. So with the other 1-6 probability, we already know what order it is because we moved the 6 on the first shuffle. So that's 6, 1, 2, 3, 4, 5, 7. And so here again we can ask, that is a 2, not a 3. What happens if we move different cards here? So if we move the 2, then 6 is on top of the 3. If we move the 4, the 6 is on top of the 3. We can't move the 6 because the 6 is on top. But we can see still that any one of the rest of these cards, so 1, 2, 4, 5, or 7, if you move any of those 5, the relative position of 6 and 3 will remain the same. But if we move the 3 to the top, then 3 will be on top of 6. So that will mean that with 5-6 probability, the 6 is on top. And with 1-6 probability, the 3 is on top. So you notice that these numbers 1-6 and 5-6 are coming up. So you might want to think, well, what happens with probability 5-6 and what happens with probability 1-6, right? So here you can see that what happens with probability 5-6 is that the order between 3 and the 6 remains the same. Now you only care about the order between 3 and 6 and you don't care about any of the other numbers. So that's what you want to focus on. And so here, for example, with the 5-6 probability, 3 started on top because 3 is on top of 6, obviously. And 3 stayed on top with 5-6. Here, again, 3 stayed on top with 5-6 and it changed with 1-6. Here, 3 started on top, it changes with 1-6 probability to become 6 on top. And then 6 stays on top with probability 5-6, and 6 switches to 3 on top with probability 1-6. So how can you convince yourself that this is always the case? Well, suppose like one of the two 3 or 6 is on top, then that means that the other one will be in one of the 6 lower cards. And the only way to switch the position is to choose the lower of them and that's always possible because it's never the top card, because it's on the bottom between 3 and 6. And so you can always choose, like with 1/6 probability it'll switch, and with the 5/6 probability it'll stay on top. So you can work out a few more examples of that if you're not convinced. But that means that we can rephrase the question of after 10 shuffles, what's the probability that the 6 is on top, as saying this. So let's say that we take 3 shuffles, right? And so we start off with 3 on top, so this is like the 0 shuffle. And then 1, 2, 3. Let's say that we have a 6 on top, a 3 on top, and then 6 on top. So we can choose some other things as well. So for example, we do 3, 6, 6, 3, or we can do like a 3, 3, 3, 3, a simple case. And then we can look at how many switches do we have here. Here we have 1 switch, 2 switch, 3 switches. Here we have 1 switch, not a switch, 2 switches. Here we have no switches at all. So it's pretty easy to see that if you have an even number of switches, then you're going to switch an even number of times between 3 and 6, and you're going to end up back at 3. However, if you have an odd number of switches, then you're going to switch an odd number of times between 3 and 6, and you're going to end up at 6. And that doesn't matter that we chose 3, we can also choose 4, and it's the same sort of thing. So for example, this one now has 1, 2, 3 switches, so it's odd number of switches, so it ends in a 6. This one has 1, 2, 3 switches, so it also ends in a 6. This one has 1 switch, which is odd, so it also ends in a 6. And if this was like a 3 at the end, there'd be 0 switches, and anyways. So now we can ask, like, let's say that we have 10, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And to each of these, we can either assign like switch, not switch, switch, not switch, 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 not switch, 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 not switch. So for example, this would be like 3, 6, 6, 3, 3, 6, 3, and so on. And so for every sequence of like switch and not switch, we can construct a sequence of whether 3 or 6 is on top. And we know that if the n number is 6, then we have an odd number of switches. So what we want to ask is, for each switch, what is the for each like sequence of shuffles, what is the probability that you have an odd number of switches? And so how many ways are there to have, for example, n switches out of 10 total shuffles? So that'd be 10 choose n. And what are the probability that n of them are switches? That would be 1/6 the probability n, because each switch happens to the probability 1/6, and you have 5/6 to the 10 minus n, so that the rest of them are not. So for example, if you were to have 6 switches and 4 that weren't switches, you can have 10 choose 6 possible ways to arrange those 6 switches, and each of those 6 you would have to have a 1/6 probability that they do switch, and each of the 4 you would have a 5/6 probability that it doesn't. And we want to take the sum of this over all n odd. So that'd be like n equals 1, 3, 5, 7, and 9. Okay, so how could we possibly evaluate the sum? Seems kind of messy. Well, notice here that we have 10 choose n, something to the power of n, something to the power of 10 minus n. So that should remind you of the binomial series, like 1/6 plus 5/6 to the n. This will be the sum from n equals 0 to 10 of 10 choose n, 1/6 to the n, 5/6 to 10 minus n. And so what we can do is, well, we want to sum over all of the ones of these where n is odd, and we can do that using a roots of unity filter by introducing an extra variable. So what we'll do is we'll put in a little x here, so it's 1/6 x plus 5/6 n, and so that will just mean that we, instead of doing 1/6 to the power of n here, we have x over 6 to the power of n, or we can rewrite that as just being 1/6 to the power of n times x to the power of n. And so the advantage of doing this is that now we have a variable here, and we have some coefficients to the variable, so it's just like some sum a0 x to the 0, a1 x to the 1, plus so on and so forth. And we want to sum over all the odd coefficients, so a1 plus a3 plus a5 plus a7 plus a9. And so if you watch my video on roots of unity filter, or if you just know about roots of unity filter, then you know that the formula to do that is, let's say this is equal to f of x. So since we're taking the sum of k is congruent to 1 mod 2 of a sub k, this will be equal to 1/2 because we're taking mod 2 times the sum over the square roots of unity, so it'll be x squared is equal to 1, or this is just x is equal to plus or minus 1 of f of x. So what that means is that this sum over here, we're filtering out of this all the ones which are 1 mod 2, and that will be 1/2 of this sum of f of 1 plus f of minus 1 times this. Or actually no, sorry. This is times x inverse, because you're taking all the numbers that are 1 mod 2 instead of 0 mod 2. So if it's 0 mod 2, you just have f of x, but since it's 1 mod 2, you have x inverse. So now let's evaluate this. So that'll be 1/2 times, well, what's f of 1? That'll just be 1/6 plus 1/5 to the power of 10. Should be 10, not 9. And then x equals -1. That will be x inverse, so -1 inverse is -1. So it'll be minus 5/6 minus 1/6 power of n. So I just wrote 1/6 afterwards because it's 1/6 times -1, and then you subtract that off. Why do I keep writing n? It's 10. And so this will be, this is just 1, so that's 1 to the power of 10. So that's just 1. And subtracting off 1/2 times whatever this is. So this will be 4/6, which is 2/3. So this will be 2/3 to the power of 10. And, well, that's just your answer, because this is equal to this sum, which we said was a sum that, the probability that you have an odd number of shuffles, and the probability that you have an odd number of shuffles is the same probability that you end up with 6 on top. And so just as a little sanity check, you can see like, this is slightly different than 1/2, because 2/3 is a number less than 1, so if you take a number less than 1 and raise it to a high power, it's approximately 0. And so this is like slightly different from 1/2, which makes sense because you expect that the probability that you have a 6 on top of a 3 is approximately 1/2, because like you have the probability that 3 is on top is also roughly the same probability. So yeah, that's a nice solution to this problem, which use generating functions to evaluate this really nasty sum. Yeah.